Okay, so when I woke up this morning thinking about what I was going to say today, which invariably one does on these occasions, it occurred to me that it's 40 years almost to the day since I wrote my first line of SQL code. In those 40 years, the world's changed dramatically. There was no internet, no mobile phones, no social media. We live in a world now full of interconnected, complex, sophisticated data. The challenge of finding insight in that data is harder than ever before. My journey with graphs started somewhat later. I've been using graph databases, writing Cypher, Open Cypher, and GQL code for about 15 years. And it's true to say that when I first started using graphs and understood the power, it was a revelation to me. So my name's John Swain. Today, I'm going to talk to you for the next 30 minutes and share, hopefully, some of my passion for graph analytics and graph databases and the vision that we've got at Google for how you can be enabled to deploy the same kind of analytics. So the first question is, why a graph and what is a graph? Well, a graph is a simple representation of entities called nodes and the relationships between them, sometimes called edges or relationships. The key thing about graphs is it's optimized for understanding the nature of the relationships between the edges. This gives us extreme power to understand how things connect, the influence and relevance those connections have. The graph that you're looking at here is a classic social graph. So the nodes are people, other people, how they're connected, their skills, the groups that those people have. There are lots of other types of graphs and graphs applications. For example, in retail, the relationships between people, purchasers, marketing campaigns, support calls, etc., helps to build and give us that insight into customer 360 and loyalty, etc. Financial transactions, accounts, payable accounts, the people, the ownership of those accounts, the transactions and payments between accounts, lets us understand the flow of data and potentially detect fraud. In IT and network of physically connected devices, the edges and the relationships and the costs between them help us understand weaknesses, potential failure hotspots and performance issues. We've briefly covered social networks, which is, I guess, a classic example of graphs, and there are many other use cases. Question that I get asked a lot when talking about graphs is, why can't we do this with SQL and relational databases? And the answer to that is, to some extent, and in theory, you can. You can model the same entities and relationships using tables and joins in a relational database. However, it gets complex very quickly. And here's an example of the kind of query that we're very good at asking as human beings. So find a person, find the friends of that person, the friends of the friends of that person, and find the posts they've made referencing countries that neither of those people live in. It's quite a sophisticated query, as I say. We can easily articulate as a human being. It's quite complex to translate that into a query. However, on the bottom left here, you can see how you translate that into a query using a graph query language, in this case, GQL, which we'll come on to more later. And on the right-hand side is the equivalent in SQL. you can start to see just how complex it becomes to model these kind of entities in SQL versus a graph. This is a pretty simple graph query. So what's the solution to enable you to use the power of graphs? Well, graph databases. Graph databases are optimized for storing and traversing those relationships rather than using joins. They support specialist graph query languages like the GQL you've just seen, and allow us to gain insights from the connectedness within the data. Another question, a good question about graphs, and something I think about quite a lot, is why graph databases are not more common than they are. Given the power, the simplicity of modeling real-world entities and relationships, why is this not deployed more frequently and more commonly used? And there are three key reasons why. One is the operational overhead. Conventionally, graph databases require specialized implementation, specialized setup, specialized management. They typically have scalability limitations. So they either become prohibitively expensive or simply don't scale to the levels that you might require for very large graphs. And lastly, importantly, there's a steep learning curve, and there's not as much expertise around in graph query languages, in graph expertise, as there is in conventional analytics. As I'm sure most of you know, Google has a long history with graphs. I wouldn't be standing here talking to you as an employee of Google if it wasn't for a graph algorithm called PageRank. It's a play on words of Larry Page's surname and a web page. And Larry Page had the insight to convert an existing algorithm by making it work for web pages. It's one of those things when you see how it works that you think, why didn't I think of that? But it also illustrates the power of graphs. There's more complexity to it than that. But it was a fairly simple change that unlocked the power of graphs. Graphs at Google are used, obviously, still to this day to support the search engine. But the knowledge graph panel you see on the side of search comes from our global knowledge graph. We use graphs for network optimization, for fraud detection in ads, for example. Our vision is to bring the power and our expertise in graphs to everybody else through a unified graph solution. Based on two services, existing services, Spanner Graph and BigQuery Graph, to cover the full spectrum of graph use cases, from real-time interactive low latency queries for which you would use Spanner Graph, through to very, very large scale graph analytics capabilities through BigQuery. This is a unified solution with the same experience of schema management, interface, query language in both platforms, and smooth or no data flows between the two systems. One of the obstacles to graph deployment is that data movement, moving data from conventional sources, building a graph, deploying it, and writing it into a graph database. Our vision is to minimize the cost of that. So it's reimagining a graph database, as I say, through a native experience, delivering the ability to query in GQL, integrated with SQL. So you can run graph queries and SQL alongside each other. Search on graphs, important. I'll touch on that a bit later. And as you might expect from Spanner and BigQuery, very large, unlimited scalability and optimized performance. How does it work? In these 3 steps is simply how you deploy a graph in BigQuery or Spanner. So firstly, you create a graph schema. Secondly, you can then query that graph using the ISO standard GQL language, and then within the interface for BigQuery and Spanner, visualize the graph results. So I'll quickly walk you through that. Creating a graph schema, let's assume we've got these three tables. We create an account, person, own, and transfer table. And this is a graph creation. We simply create a map to define a property graph with node tables for the account and the person, and edges for the transfer and the ownership attributes, relationships between the person and the account. It's called create property graph. The type of graph that BigQuery and Spanner support is a labeled property graph. And this is what that graph looks like. So once we've done that, the data stays where it is. It's queried from the source tables, but we can run a graph query. So here, an example of a very simple finance graph query in GQL. You'll notice the first line is defining the graph that we're going to use. BigQuery and Spanner support multiple graphs on the same database, so we just define which graph we're going to use for each query. And then we use this syntax, ASCII art syntax, where we're matching nodes via relationships. The brackets denote the nodes, and the square brackets and the arrows define the relationships. So here's the interoperability with graph and SQL. What's highlighted in red is the same query as the previous screen, but now embedded into a conventional SQL query. So we can see we're selecting from the same GQL, which we define as a graph table. The rest of the SQL query just sees that subquery as a regular table, and we can join it with other tables. So in this case, we're searching for this person, Jacob, for the accounts that he owns and repayments on those accounts. And we're joining it with a SQL table, customer audit logs, to return information from both places. I found this much more powerful than I expected. When I first learned about the way this was being deployed on BigQuery and Spanner, I thought, well, I've been writing OpenCipher, I can learn GQL, why would I need to interoperate? I've actually found it really powerful. And it's all the more powerful in that most organizations have got a lot of existing SQL skills, less skills in graph query language. So the ability to interoperate and allow your SQL programmers to consume graphs created by someone else is really powerful. Graph search. So if you think about a common graph rag pattern that we're seeing, so graph rag is enhancing a conventional AI rag pattern by retrieving the context from the graph rather than from other typically semantic searches. That might start with identifying a specific entity within the graph. And typically in conventional graph databases, that kind of search capability is not native, it's bolted on, it's not a native capability. With Spanner and BigQuery, you get the power of semantic search, vector search, and regular text search built in as part of the product. And that's really important in finding the starting point for those graph queries that you want to run. Here you can see we're just using the where search to match a text string. We're looking for a description on a customer that's got some text with diverse portfolio. And lastly, visualize graphs. So in Spanner Studio, in BigQuery notebooks, and in Colab and Jupyter notebooks, you've got the ability to run these queries and do some basic visualization. We also have Integrations with third-party visualization tools for more sophisticated visualization needs. I'm going to show you very quickly an example with G.V later. So interoperability. The use cases for Spanner and BigQuery are Spanner is for low latency real-time queries, a Spanner for analytics queries. But the data you might want to query might live in both places. So the vision here is that you can run queries in both places with very little integration. Within BigQuery, you can define a Spanner graph as an external source and create a graph over both sources, run a single query that will bring the results from Spanner and from BigQuery. The ETL and reverse ETL processes between them are extremely efficient. What we're doing here is minimizing the amount of data movement and the amount of data engineering required to effectively deploy graph solutions. And a summary of the differences between Spanner and BigQuery. Spanner, they share a unified interface, common language, and an interface. Batch versus online and operational workloads. Latency values typically milliseconds to seconds in Spanner and seconds to minutes to hours depending on the scale of the queries in BigQuery. Traverse graphs starting from a single node would be a typical pattern in Spanner, and traversing or analyzing graphs with millions or billions of nodes would be a typical pattern in BigQuery. The freshest data is in BigQuery in Spanner, and long-term analytical data is going to be in BigQuery. Spanner graph is currently in production, available to use right now. BigQuery graph is in private preview, going public previews soon. But we already have customers using both in production, including Virgin Media, Snapchat use this for social media analytics. There's a very interesting company called BioCortex using BigQuery graph to analyze proteins and diseases and drugs to find cures for cancer. So the title of this talk was Graph and AI at Scale. How our vision is also to we're bringing the graph to the data. This is what we've looked at so far. Our vision is to also bring the AI capabilities to the data, to make that as simple as possible at scale. And I'm going to run through a quick demo to show you how this comes together. It's based on a data set called GDELT, which is available as a public data set in BigQuery. It's refreshed every 15 minutes. Hundreds of thousands of global media sites translated into English from however many languages. 21 billion words of academic literature and captioning in near real time of video sources, all published in BigQuery. When you turn that into a graph, here's an example of the news on September the 11th, a couple of weeks ago. What I want to illustrate is the power of graphs and how quickly we can deploy that in BigQuery and Spanner. Immediately by creating this graph and creating this visualization, you can start to see what was important in a whole day's news across the whole world. The clusters and the sizes give you an idea and an ability to evaluate what's going on. The news on that day wasn't particularly uplifting, so I'm going to focus on this part of the graph that caught my attention. So I'm not a particular David Bowie fan. I knew nothing about this. I just saw that word, thought, okay, let's have a look at that. Interestingly, if you take this picture and basically chuck it at Gemini with a little prompt to say, what was this about on September the 11th? It does a pretty good job of going away, researching it, finding all the links, piecing together what the stories and why people were related. That gives us a glimpse of the power of Gen AI applied to graphs. So what we want to do that is in a bit more structured way and at scale and repeatable pattern. So in the GDELT data, there's information about people, articles, themes, URLs, events, and you might build a complex graph starting to become complex like the one on the left. However, I just want to illustrate the power from simple graphs. All I'm interested in here is creating a simple graph on the right that is the co-occurrence of people in the same article. So it just records, it's just the two people, one co-occurs with the other in the same article. And we're going to build a graph based on that. The source data, this is a table on the left-hand side that shows all the data that's collected by GDELT, and you'll see the themes and the people information is densely packed into those tables. So these are relational tables, but there's no normalization. They're just text fields with a particular format. We can run queries to extract information in a conventional way. It's pretty complex. So if we create a graph over that data, as I showed you before, we're simply creating two tables, one for the person and one for this relationship called co-occurs with. And we're creating the tables and then defining the nodes and the edges for those two entities. Then we populate that graph. It's a little bit more complex, but it's basically an insert from the source GDELT table into those two entities. The data in GDELT, as I say, is a little bit complex, so there's some unnesting and some unpacking of that data, and we create the graph. Once we've done that, and that's it, we're then able to do graph things. We're able to query the graph. And here's me doing that in G.V visualization. So we can see we run a query to return just the pairs of people and their co-occurrence with a weight on that co-occurrence for the number of times that they co-occur. If we look for David Bowie, here we're looking for everybody that's co-occurs with the David Bowie person within 3 hops. And we get a result like this. And we can start to see very quickly who's related, what that story might be about, including this collaboration with Nile Rodgers. So we've got that in place. We're still left with this complex set of themes codifications. So in terms of augmenting the graph, it would be quite nice to produce a human-readable, descriptive text for each of those rows based on the themes. So again, if we take this and there's ask Gemini to write a human-readable summary of what those themes are, this is what it will produce. So to do that at scale, as mentioned before, we bring the AI to the data. Within BigQuery, we simply create a model. Here, we've given it a name and a data set. We're going to create a Vertex AI, which is where Gen AI models are hosted in GCP. And we're going to select which model and create a model that's now available to BigQuery. So it just appears here in the list of models. For this demo, which is a bit more sophisticated than I'm showing you today, I'm using different variants of the models for different capabilities. Once we've done that, to use generative AI on the columns in the database, it's as simple as running a SQL statement that selects, it's not working, but if you can see, generate text from the model that we've just created with this prompt in green. So we give it a prompt, we concatenate the information we want to pass in from the rows in the table, and it goes away, calls Gemini, and it outputs at scale every row in the table with a succinct definition. The other feature I talked about was combining GQL and SQL. Here's an example of that. We're going to select all the people in the table. In the co-occurrence relationship, I don't know if anybody noticed, but there was a property for article IDs, which is a link, a foreign key reference to another table called articles, which has the URLs of every single one of those articles. So we just do a simple join, get all the IDs from the graph. In this case, we're interested in that subset of the graph for the David Bowie community, and get all the, by just joining to the articles table, bring back all the URLs, which is a foundation for GraphRag. And just by way of example, I took those URLs, put them into Notebook LM, and immediately goes away, reads all those articles, comes back with a pretty sophisticated analysis, fully referenced back to the source articles of what the story is within that part of the graph. So we can see here, we're going to ask in a minute a suggested question, which was about the personal archive, gives us a summary of that, linked back to the URLs with that source information. So hopefully I've shown you there a very simple way, which I think is important, that we can start to create insight from chaos. No presentation would be complete today without a nano banana generated image. I just asked it to generate an image to summarize that story. So make your own mind about how good you think that is. So just to wrap up, our vision is a unified graph solution with these elements based on Spanner Graph and BigQuery Graph to meet a set of use cases that span everything from real-time, low-latency, interactive queries to very large-scale analytics. What we'd love to do is explore your use cases with you. So on the left-hand side, there's a sign-up for the BigQuery Graph preview. If you complete that, we'll be in touch with our product managers for BigQuery Graph, and we'd love to explore the use cases that you've got. We've got a very clear vision for what we see as the value from doing it this way. It's not going to match every single use case, but for the ones that it does, it's going to be really powerful. The link on the right just takes you to Spanner, which is currently in production. You can start using that today. And that's it from me. Feel free to buttonhole me after this session if you've got any questions, or we'll all be on stand K40 for the rest of today and tomorrow. Thank you.